This is the first video over Chapter 18, Linear Independence. I'm going to break this chapter into two parts. The first example that I'm going to do, example 192, we're going to investigate whether or not sets of vectors are linearly independent just from the definition of linear independence, and also we will use corollary 191. So for part A, we have these three vectors, which you'll notice are just I, J, and K from R3. So let's suppose that we have scalars A, B, and C such that A times this vector plus B, 0, 1, 0, plus C times vector 0, 0, 1, which we typically call K, is the zero vector. Then what does that mean? Well, if you add these three vectors together, you have A, B, C is equal to the zero vector. This implies that A equals 0, B is equal to 0, and C is equal to 0. Therefore, the set is linearly independent. Continuing to part B, for B, we have the set of vectors 1, 0, 0, 1, 1, 0, and 1, 1, 1. So first of all, let's suppose we have A, B, and C in R such that A times the vector 1, 0, 0 plus B times the vector 1, 1, 0 plus C times the vector 1, 1, 1 is the zero vector. Supposing that's true, then when we add these three vectors together, what do we get? We get a vector whose first component is A plus B plus C. The second component is B plus C. and the third component is C. And now we can, when we look at this, we can first of all see that C is 0. Well, since C is equal to 0, and B plus C is also equal to 0, B is equal to 0. And finally, if B and C are both 0, and A plus B plus C is 0, then A is 0. Therefore, the set is linearly independent. Continuing to part C, we have a set of two vectors. This is the part where we will use corollary 191. Notice that the set that contains just this vector alone is linearly independent. And so by corollary 191, we only need to check to see if one of these vectors is a linear combination of the other, which is not the case. So note that there is no alpha in the reals such that alpha times the vector 1, 0, 0 is equal to 1, 0, 1. Because alpha times this vector is going to be alpha 0, 0, and the third component will not be equal to 1. So, by corollary 191, the set is linearly independent. The last example that I'll do in this video is part D. Part D, we have the set of vectors 1, 0, 0, 1, 0, 1, and our third vector is 3, 0, 2. This set is going to be linearly dependent. Note that 2 times the vector 1, 0, 1 plus 1, 0, 0 is equal to the vector 3, 0, 2. Since one of the vectors in the set is a linear combination of the other two, then the set is linearly dependent. Therefore, the set is linearly dependent. If you took 2 times this vector plus this vector minus this vector, it's equal to the 0 vector. I'll just write that out. 2 times the vector 1, 0, 1 plus 1, 0, 0 minus 3 times the vector, just times the vector 3, 0, 2. Is the 0 vector in R3. So we can take vectors whose coefficients are not all 0. So we have 2 times this vector plus 1 times this vector minus 1 times this vector is a 0 vector. So this set of vectors is linearly dependent.